All right. Hello, my name is Brock Abramson. Today I'm going to be bringing up the data. Now, if you just give me 1 second here. Okay. Today we're actually going to be looking at the stabilization energy in benzene. These are the three molecules that we're going to be looking at here. The benzene, cyclohexane, and trans cis cyclo decatrin. So we're actually going to be studying the reaction here, comparing it to other methods such as Sigress. One of the interesting qualities about this reaction is that the CDDT has the same amount of bonds as cyclohexane and benzene combined. This is going to actually be direct whenever you're studying the energy released by this reaction. It's going to be directly correlated to the energy stabilized by the aromatic conjugated benzene ring. Simply because the CDDT, while it is conjugated, does not have the aromaticity like benzene. Cyclohexane just has the is not aromatic as well. So whenever you're finding the heat release Q, that's going to be equal to the delta U here through this equation 2. And then you can use delta U to find delta H through equation 3. Now, whenever you're finding delta H, it's actually going to be related here through Hess's law. So in Hess's law, A, B, and C are going to be given by literature values. F is going to be found by this figure here, which we're going to be looking at later. But D and E, we're actually going to be finding through experimentation. It is worth noting that in this case here, we're going to be finding the enthalpy through this. Now, this is actually through the natural log of the pressure here and its correlated temperature. So we'll be looking at that again in a second. Our two hypotheses is that the Sigress is actually going to generate the most accurate resonance energy values, has no experimental human factors, and it's run by computer software. So it should be the most accurate. The experiment resonance energy for benzene should be higher as well, because some may stay in the liquid form, which has a higher resonance energy. And this is just through natural experimentation. So whenever you're looking at the actual method here, the fuse wire that you'll see here is connected to a sample basket, which has either the cyclohexane or the CDDT in it. It's worth noting that the cyclohexane was in a capsule, so we had to remove that heat of formation or combustion from the both the capsule and the wire from the total heat release in order to find just the cyclohexane. So this part was put into this capsule or this vessel here, the oxygen combustion vessel. So this was then thrown into the oval bucket, which is then thrown into this calorimeter. From the calorimeter, you clamp it shut here with these, and then you run a current through it, ignite it, and measure it on the computer. And this was used with, again, the BombCal software. So whenever you're actually looking at the spectra here, it's going to give you a spectrum of temperature versus the relative time. We're going to be looking at the values that we need for that. With Sigress, these are the molecules that we use to study, again, benzene, cyclohexane, and CDDT. Now for each of the runs, we had cyclohexane run 1, cyclohexane run 2, CDDT run 1, CDDT run 2. I'm going to be doing this for a couple of these, so it's related to all four the same runs. So looking at these time values, we're going to be looking at 5. So TI here is the initial temperature, about 1 minute after the stir is turned on, no ignition yet. But whenever you're looking at TA, that's when it's actually ignited, sharp increase in temperature. TB is whenever we're going to be looking at 60% of that final temperature. The final temperature is going to be 452, or in this case, 452 seconds, but that's where it actually reaches its maximum temperature. TF, it's either 90 seconds after it reaches its max temperature, or the very end of the graph whenever it stops collecting the data. So that's what we used for all of these values, which I'll include in a further table. Also included in that table is the R1 and R2 values. They were used in the determination of the delta T. So R1 in this case is correlated to the slope of each of these lines. In this case, the R1 is directly related to the Ti and Ta values. So the slope right here, that's what's magnified in this case. Now, the same concept applies though for whenever you're looking at the Tc to Tf, which is the final temperature that's up here. That's also the slope that you see. All of these values are included. Both the temperature, the time, and the R values for each of the runs is included in this table here. These are each of the individual values. These were then used in the determination of the change in temperature. That's through this equation right here, Tc minus Ta minus R1 MSB minus R2 C plus B. This is the sample calc, so this is how you found the 3.881 value for cyclohexane run 1. Now the Q total, that's here. It's related directly through this equation. Now with the sample, you have to do the Q total minus the heat for the wires and the heat of the capsule, because this is for the cyclohexane. This is not existent for CDDT. So that's where you find the negative 4,083.77 value. That's right there. The enthalpy, you then use that direct relationship that we discussed in the first right here to find the negative 4,091, and these were averaged to find that. These were then used in Hess's law, which again is this equation here. Again, A, B, and C were literature values. F was found from that spectrum, directly relating the pressure and temperature to the enthalpy of enthalpy of vaporization for the CDDT. So we used that, all of these values, sum them up to find the 161.17 kilojoules per mole of for the resonance energy of benzene. This value was compared then to Sigres, and both of these were compared to the literature value here, which is 150.24 kilojoules per mole. The percent error for both the experimental and Sigres was included. These are all the rest of the equations here. So the first hypothesis, Sigres did prove to be the most accurate provide the most accurate resonance energy value. The experiment has human error. Sigres also assumes that the molecule is in a gaseous state, which you cannot perfectly have in experimentation. So whenever you're looking at the second hypothesis, the experimental resonance energy for benzene should be higher than the theoretical. That also proved to be correct. I think it just proved that some of it stayed in the liquid form, which has a higher resonance energy. Also shows why Sigres was a more accurate method. Percent error of 7.61. This is just some general notes. This showed that it could accurately measure the resonance energy of benzene. Some limitations, again, it can't directly impact the level of liquid benzene in the reaction. I think that's pretty important if you're trying to establish a very accurate method to compare it to the literature value. The effects of the rings and the aromaticity to the energy levels in this reaction, though, can still be studied. Factors such as the resonance energy of the benzene. Also, you could use different factors like studying the difference between a linear and cyclic hexene. Or even the addition of carbons to a conjugated ring, like you do in this equation, which is the combustion of COT. So, and COT in this case is cyclooctatetraene. Now, you can use this same sort of style to determine the resonance energy of benzene. This is because COT is actually non-conjugated. There's no resonance stabilization energy. The only enthalpy of formation is due to the benzene's resonance energy. So whenever you're looking at subtracting these two values, that's actually going to equal the ERES. Can bond enthalpy information be used to determine the resonance energy? Yes. Now, the enthalpy depends on the stability of the bond in the overall molecule. Whenever you have benzene's resonance energy, it's actually going to stabilize the overall structure and increase the enthalpy that's required to break one of its bonds. So, again, whenever you're comparing it to something like cyclohexane, you can just take the enthalpy for cyclohexane, subtract it from the benzene. That's just going to give you the ERES for benzene. Now, a different method that can be used, you could add 3 bond enthalpies of ethene and the 3 bond enthalpies of ethane, subtract that total energy from the enthalpy of formation of benzene, because these have the same total bonds as benzene. This should give you a resonance energy for benzene, because you're subtracting just the normal bonds from that stabilization of the benzene ring. However, that is not as accurate as either the Segrest, which we already established was the best, or the lab that we conducted. That's because that the cyclohexane and CDDT are closest to approximating the benzene's conjugated character, and cyclohexane has the most similar structure to benzene. This is also in Segrest, so that's another reason why that's the most accurate. The cyclooctatriene, I believe, is tetraene, excuse me. It's not conjugated and it's not aromatic. This is less accurate, simply put. Discussion 3 includes this, which again is the ethene and ethane that they don't have any conjugation or stabilization energy at all. They're going to be very high in energy and not the most accurate. Now, when we're comparing these molecules here, like I mentioned, you can compare situations like this, which is just a linear carbene, and you can compare it to something like this, which is cyclic and conjugated. So the first two are actually not conjugated, and they're going to have less or more energy, less energy savings than this cyclooctatetraene. Now, this is anti-aromatic, though, so it's going to have a lot less energy of stabilization compared to something like benzene, which is aromatic, perfect bond angles. It's just a ideal molecule for lower energy. And that is all. Thank you very much.